In this lecture, I am going to present what is portal frame and what is sway and non-sway frame. Then I would like to solve two problems on non-sway frame by slope deflection method. So first coming to what is portal frame. Portal frames are structure consisting of a number of members having rigid joints at their junctions. Such frames when loaded will deform in such a way that members meeting at a junction will rotate by same magnitude and in the same direction. The angle between the rigidly connected members remains the same. Look at this figure. The joint B is a rigid connection and support A and support C are fixed. So at joint B there will be rotation theta B takes place when it is loaded. But at end A and C the rotation is 0 due to fixed end. Also there is no displacement of the members AB and BC at the end A and C are fixed. So the delta that is equal to 0. So here there is only one rotational displacement takes place at joint B and the rotational displacement at joint A, that is theta A 0, and the rotational displacement at joint C, that is theta C is 0 due to fixed ends. So here only one unknowns, so that unknowns can be determined from one equation. The equation that we can take the equilibrium of joint B, that is the sum of the moment at B is equal to 0, that is MBA plus MBC, that is equal to 0. Then after solving the equation you get the rotation or the rotational displacement at B, theta B. Then after knowing the theta B or the rotational displacement at B, then you can find out the moments at all joints by putting this rotational displacement in the slope deflection equations. Then coming to what is sway and non-sway frame. If the side movement of the end of a column takes place, then the frame is called sway frame. So look at this figure. Due to the horizontal loading, here the sway takes place. Here sway takes place. The sway amount is delta. So the sway takes place, that is the original vertical member AB, so that is displaced to the member AB dash. This is the sway which takes place at B, and here also the vertical member CD, that is the joint C, displaced to the joint C dash. So this is the delta amount. So here the same delta takes place at joint B and joint C. So this is called the sway. The sway in the frame is prevented by putting the unyielding supports at the beam level. Look at this figure. So here this is the beam and this is the vertical members. So here this is the unyielding support which is present at the beam level. So due to this unyielding of support, here the sway is prevented. So there is no sway takes place. So this is the non-sway frame. And look at this figure. So here this is the vertical members and this is the horizontal members. The horizontal members is extended up to this, and here this is the fixed end. This is the fixed end. So due to this fixed end, so there is no sway takes place. Even if the horizontal load is present, but due to this fixed end, there is no displacement of the vertical member takes place. So this is also the case of the non-sway frame. And look at this figure. Here the load is present at the midpoint of the beam. This frame is symmetrical for the loading. As we concern the loading, So this is symmetrical loading. So here this is the case of the non-sway frame. And look at this figure. Here the load is present W, that is at a distance small a from the support B and small a from the support C. So here the loading is symmetrical about the central axis. Here also the sway is prevented. So this is also the example of the non-sway frame. Look at this figure. Here the load is present W on right side on the vertical member AB, and here the load W present towards left on the vertical member CD. So both the loads are equal and in opposite direction, and this is the central line. As we concern the center line or the axis, the loading is symmetrical about the axis. So this case also the sway is prevented. So this is the example of the non-sway frame. If the geometry and loading of the frame is symmetrical about the vertical axis, then the sway is prevented. Then coming to the first example, analyze the frame shown in figure by slope deflection method and draw bending moment diagram. So this is the non-sway frame. So because here the support A, that is fixed, and the support C also fixed. And the vertical member AB of length 3 meter and the horizontal member BC of length 4 meter. And the moment of inertia of the vertical member is I, and moment of inertia of the horizontal member BC is 2I. And on the horizontal member there is present the 12 kilonewton by meter uniform distributed load. And that BD, this is the overhanging portion. So at D there is present one concentrated load 20 kilonewton at a distance 1 meter from the joint B. In slope deflection method, so first you have to find out the fixed end moments by considering in each span the ends are fixed, and you have to find out the fixed end moments. So this is the vertical member, and here there is no loading. The fixed end moment at the end A and fixed end moment at the end B both are 0. MFAB 0 and MFBA 0. Then on the horizontal member BC, MFBC, that is equal to minus 12 into 4 square by 12, that is equal to minus 16 kilonewton meter. And MFCB is equal to plus 12 into 4 square by 12, that is plus 16 kilonewton meter. Then the BD overhanging portion, that you have to treat it as a cantilever portion, and you have to find out what is the moment at the joint B. So MFBD, that is equal to MBD, is equal to 20 into 1, is equal to 20 kilonewton meter. So you have to treat BD as a cantilever, and you have to find out what is the moment here, MBD, that is equal to MFBD. So these are the fixed end moments. Then coming to the end conditions, here you see at the joint A, so due to fixed end, the slope is 0, theta A is equal to 0. Then at the joint C, due to fixed end, the slope theta C is equal to 0. Here the rotation takes place at joint B, and that is equal to theta B. And theta A is 0, theta C is 0, and theta B is the unknown. And the delta, because here there is no sway takes place, so the delta is also equal to 0. Theta is 0, theta C 0, delta 0, only one unknown, that is theta B. So this unknown you can find out by using the one equilibrium equation, that is, so at the joint B, the sum of the moment, that is equal to 0, that is MBA plus MBC plus MBD, that is equal to 0. By taking the joint equilibrium equation of joint B, so you can find out this unknown rotational displacement, that is theta B. So first you write down the slope deflection equations. As you know, the slope deflection equation MAB is equal to MFAB plus 2EI by L 2 theta A plus theta B minus 3 delta by L. So here you see MAB, find out MAB, MBA, then MBC, MCB. So MAB is equal to, here theta A 0 and theta B, and delta is equal to 0. MFAB, the fixed end moment MFAB 0. So here you put MFAB is equal to 0 and 2EI by L. The vertical height of the member AB is given 3 meter. So here you put 3 meter, then 2 theta A. So here theta A is equal to 0. So this is 0, and theta B only have to take, and delta is also equal to 0. So after simplification, MAB is equal to 2 by 3 EI theta B. Then find out MBA. MBA is equal to MFBA plus 2 EI by L into 2 theta B plus theta A minus 3 delta by L. As you know, L is equal to 3 meter and MFBA is equal to 0. So MBA is equal to 0 plus 2 EI by 3 theta A. So theta A is also equal to 0. Only have to take 2 theta B. Delta is also equal to 0. So 2 EI by 3 into 2 theta B. So that is 4 by 3 EI theta B. MBA is equal to 4 by 3 EI theta B. Then find out the slope deflection equation MBC and MCB. MBC is equal to MABC plus 2 EI by L into 2 theta B plus theta C. So in horizontal member there is no need to take the displacement. Here you know that is MABC, that is equal to minus 16 kilonewton meter. So here you put minus 16 plus, and for member BC the moment of inertia is given 2I and the length is given 4. So here you put 2E into 2I divided by 4 into 2 theta B plus theta C, and you know theta C is equal to 0. Then after simplification, MBC is equal to minus 16 plus 2 EI theta B. Then find out MCB. MCB is equal to MFCB plus 2 EI by L into 2 theta C plus theta B, that is, and MFCB that you got 16 kilonewton meter, 16 plus 2E into 2I by 4 theta B plus 2 theta C. Then after putting the value and theta C is equal to 0, so here you get MCB is equal to 16 plus EI theta B. Then take the equilibrium equations of joint B, that is the summation of moment at B is equal to 0. So MBA plus MBC plus MD is equal to 0, and you put the value of MBA plus MBC plus MBD in this equation. Then after putting this one and after simplification, so here you get EI theta B is equal to minus 1.2. Then after knowing this value EI theta B, you put this value in the slope deflection equation. These equations, you put the value in these equations, then you get what is the value of MAB, MBA, MBC and MCB. So MAB is equal to 2 by 3 EI theta B. So EI theta B is equal to minus 1.2. 2 by 3 into minus 1.2 is equal to minus 0.8 kilonewton meter. And the MBA is equal to 4 by 3 into minus 1.2 minus 1.6 kilonewton meter. MBC is equal to minus 16 plus 2 minus 1.2 minus 18.4 kilonewton meter. And the MCB is equal to 16 plus into minus 1.2, that is equal to 14.8 kilonewton meter. Then after getting the final moments MAB, MBA, MBC, MCB, then you give the direction of the moment. And you know how to find out the free bending moment diagram. So you know for span AB there is no loading. Here the free bending moment diagram is 0, and for span BC there is having the uniform distributed load. So here the free bending moment diagram, this is parabolic or this is also the positive bending moment diagram or free bending moment diagram. This is parabolic. So this is, you can find out, you know, that is W L square by 8. So W is given 12 and L is given 4. 12 into 4 square by 8. This is the maximum positive moment at midpoint of the span BC. So the maximum positive moment at midpoint of BC is equal to 12 into 4 square by 8 is equal to 24 kilonewton meter. The clockwise end moments are positive and anti-clockwise end moments are negative. These are marked in the figure. So bending moment diagram drawn by taking tension on dotted side as positive and tension on other side as negative. Look at this figure. So this is the tension inside dotted side. So this is, you take positive. So first you give the direction of the moment here. Here M may be minus 0.8 kilonewton meter. This is anti-clockwise direction. And MBA is equal to minus 1.6 kilonewton meter. So this is also anti-clockwise direction. This is also anti-clockwise, BA, anti-clockwise. And MBC is equal to minus 18.4 kilonewton meter. This is also anti-clockwise direction. This is 18.4 kilonewton anti-clockwise. Then MCB is equal to 14.8 kilonewton meter. So this is clockwise due to positive moment, clockwise. So these are the direction of the moment. Here MBD, so this is also, you got here 20 kilonewton meter. So 20 kilonewton means this is positive, clockwise. So this is positive and so the direction is clockwise. So here you see this 2 is anti-clockwise, this is clockwise. So the sum of the moment at joint B is equal to 0, because here this is 18.4, this is 1.6, this total is equal to 20 and the clockwise moment is also 20. So the sum of the moment here is 0. So then you draw the bending moment diagram. If the error mark outside, so you take this side 0.8. If the error mark inside, so here you take, this is 1.6, and here this side take 18.4 and this side take 14.8 and here this side take 20. Here this one, this side 0.8 and here take inside 1.6 kilonewton meter and here this is 18.4 and this is 14.8 and join these lines. So this is negative moment for span BC and this is positive and negative. Inside take positive and outside take negative, and here due to the overhanging portion, so this is the 20 kilonewton meter and join these 2 points and this is also negative. Then over the negative bending moment diagram, so draw the free bending moment diagram or positive bending moment diagram. Then this portion is cancel each other due to positive and negative, and here this is negative and this is negative and this is positive and this is also negative, and this side you take positive, inner side take positive tension, and outside you take here this is negative. So this is the bending moment diagram of the frame. Then coming to the second example, analyze the frame by slope deflection method and draw bending moment diagram. The flexural rigidity EI is same for all the members. So this is also the example of non-swept frame. So here this is A, B, C, D, and BD is the vertical member and AB, BC is the horizontal member. Here the support C is simply supported and support A is fixed and support D is fixed, and the span length of AB is given 4 meter and span of BC is given 4 meter and the vertical height of BD is given 4 meter, and on the span AB there is present one concentrated load 120 kilonewton at the midpoint, and on the span BC there is present the uniform distributed load 30 kilonewton by meter throughout the length, and solve the problem by slope deflection method. So as you know, in slope deflection method, so first step to assume the end of each span as fixed and find out what is the fixed end moments. So first you take the span AB, you have to assume the both ends are fixed, and you have to find out the fixed end moments MFAB and MFBA. Then for span BC you have to find out MFBC and MFCB, and for span BD you have to find out MFBD and MFDB. But in vertical member BD there is no load, so here MFBD and MFDB is equal to 0. But on the horizontal span AB, so here the load is present at the midpoint, so here MFAB is equal to minus WL by 8. So W is equal to 120, L is equal to 4. So minus 120 into 4 by 8. And MFBA is equal to plus 120 into 4 by 8. Then for span BC, so here due to UDL, the fixed end moment at the end B, that is MFBC is equal to minus WL square by 12. So here W is given 30 and L is given 4. Minus 30 into 4 square by 12, and the MFCB is equal to plus 30 into 4 square by 12. So these are the fixed end moment. MFAB minus 120 into 4 by 8 minus 60 kilonewton meter, MFBA plus 60 kilonewton meter. MFBC minus 30 into 4 square by 12 is equal to minus 40 kilonewton meter, and MFCB is equal to plus 40 kilonewton meter, and MFBD and MFDB is equal to 0, because here there is no loading. These are the fixed end moments. Then what are the end conditions? So here you see, as the end A is fixed, here the slope is 0, and at end D also the slope is 0. Only the rotation takes place at joint B and joint C. So here you have to take theta B and theta C. Theta A is equal to 0 and theta D is equal to 0, and here delta is also equal to 0, because the sway is prevented. So theta A and theta D is 0 due to fixed ends, and delta is equal to 0. Only you have to find out the unknown theta B and theta C at B and C. Here you need two joint equilibrium equation. So you have to take one joint equilibrium equation at B and another joint equilibrium equation at C. So you have to take the summation of moment at B is equal to 0 and the moment at C is equal to 0. That is, at joint B, the sum of the moment, that is equal to MBA plus MBC plus MBD is equal to 0. And at C, the moment, that is MCB, is equal to 0. So by using these two equilibrium equations, so you can find out what is the unknown rotational displacement at B and C, that is theta B and theta C. First find out the slope deflection equations for each span. So this is the slope deflection equation. MAB is equal to MFAB plus 2 EI by L, 2 theta A plus theta B minus 3 delta by L. So you know MFAB is equal to minus 60 plus 2 EI by 4 for AB. The span length is given 4, and here 2 theta A plus theta B, and delta is also equal to 0, minus 0. Here also you know theta A is also equal to 0. So here you put the value of theta A, also 0. After putting this value, so MAB is equal to minus 60 plus 0.51 IE theta B. Then MBA is equal to MFBA plus 2 EI by L into 2 theta B plus theta A minus 3 delta by L. But here this is delta is equal to 0. So here theta A plus theta B, theta A is also equal to 0. Only you have to put MFBA, that is 60, and L value that you have to put 4, 60 plus 2 EI by 4 into 2 theta B. So after simplification, the expression MBA is equal to 60 plus EI theta B. Then MBC is equal to MABC plus 2 EI by L into 2 theta B plus theta C. So here 2 theta B you have to consider, and theta C also you have to consider. and MFBC, that you know here minus 40, so put this value in the expression, minus 40 plus 2ei by 4 2 theta b plus theta c. So then after simplification, MBC is equal to minus 40 plus ei theta b plus 0.5 ei theta c. Then MCB is equal to MFCB plus 2ei by L into 2 theta c plus theta b. So here you have to consider both theta b and theta c unknown, and you have to take L is equal to 4 and MFCB is equal to 40 kilonewton meter. So 40 plus 2ei by 4 into theta b plus 2 theta c, so is equal to 40 plus 0.5 ei theta b plus ei theta c. Then take the vertical member BD and find out MBD and MDB. So MBD is equal to MFBD plus 2ei by L into 2 theta b plus theta d minus 3 delta by L. As you know, the theta d is equal to 0 and theta b is equal to unknown and delta is equal to 0, and you know MFBD is equal to 0. MFBD is equal to 0. So after putting this value, so here you get MBD is equal to ei into theta b. Then find out MDB. So MDB is equal to MFDB plus 2ei by L into 2 theta d plus theta b minus 3 delta by L. So delta is equal to 0 and theta d is equal to 0. Only have to take theta b value here, and MFDB is also equal to 0. So put this value. So MDB is equal to 0 plus 2ei by 4 theta b plus 2 theta d is equal to 0.5 ei theta b. So these are the slope deflection equations, and these are the equilibrium equations. Summation of moment at B is equal to 0, MBA plus MBC and plus MBD is equal to 0. So put the value of MBA plus MBC plus MBD in the equilibrium equations and get the equation 1. Then the another joint equilibrium equation, summation of moment at C is equal to 0, that is MCB is equal to 0, and put the value of MCB here, and this is equation 2. Then after simplification of equation 1 and 2, so you get ei theta b is equal to 0 and ei theta c is equal to minus 40. Then you put the value of ei theta b and ei theta c in slope deflection equation. You get, so what is the moment MAB, MBA? MAB is equal to minus 60 kilonewton meter, MBA is equal to 60, MBC is equal to minus 60, MCB is equal to 0, MBD is equal to 0, and MDB is equal to 0. These are the final end moments. You can find out what is the maximum positive moment on the span AB, maximum positive moment on the span BC. On span AB there is present the concentrated load at the midpoint. So here the maximum positive moment is equal to 120 into 4 by 4, WL by 4, 120 into 4 by 4. So this is equal to 120 kilonewton meter, and here the free BMD is triangular, and as the load is present on the span BC is UDL. So here the free bending moment diagram is parabolic. Maximum positive moment at the midpoint of the span BC, that is equal to WL square by 8. So W is equal to 30 into 4 square by 8. So this is equal to 30 into 4 square by 8 is equal to 60 kilonewton meter. So this is the maximum positive moment at midpoint of BC, and the maximum positive moment at midpoint of AB, this is WL by 4. 120 into 4 by 4 is equal to 120 kilonewton meter. Here you know these are the moments, the support moments. So here you give the direction of the support moments. Here you got MAB, this is negative, so this is give the direction anti-clockwise, and MBA you got here positive and you give the direction clockwise, and MBC got negative, so give the direction anti-clockwise. So the sum of the moment, and MBD, this is equal to 0, so there is no moment here, and MDB is also equal to 0, here also there is no moment. So here you see the sum of the moment at B is equal to 0, and MCB is also there is no moment. These are the moments, the support moment. Then draw first the negative bending moment diagram. So here you take 60 and here also you take 60 and here 0. Join these 60, 60 and 0. So these are the negative bending moment diagram. Then you know the free bending moment diagram for span AB and for span BC. So for span AB, this is triangle and the maximum positive moment is at the midpoint 120 kilonewton meter, and on the span BC the maximum positive moment is 60 kilonewton meter at the midpoint. This is parabolic and this is triangle. Then take the negative and positive overlap each other, and the overlapping portion is cancelled, and the rest things, this is the final bending moment diagram. So here this is negative, this is positive, this is negative and this is positive, and here there is no moment, bending moment diagram is 0. So here you can find out what is the positive moment, because here you take this total, here this is 60 kilonewton meter, this total is 120 kilonewton meter, so 120 minus 60, so the maximum positive moment on the span AB at the midpoint, that is equal to 60 kilonewton meter. Similarly here this is 60 and here this is 0, this is negative, and here you have to find out what is the maximum positive moment on the span BC. So here you take one ordinate, here you take, this is one triangle, this is another triangle, and find out what is the ordinate, this one. Then you know the total ordinate here 60 kilonewton meter, and find out this ordinate. The 60 minus this ordinate is equal to the maximum positive moment on the span BC at the midpoint. So this way you can find out what is the positive moment on span AB and span BC. So this is the final bending moment diagram of this example. Now all are clear. So how to solve the non-sway portal frame by slope deflection method.